Yes or no, or false or correct, all right? The second part is actually single choice problem, but we have for each of those problems, it involves numerical calculations, and you have to choose a right answer for A possible options, okay? But the problem of that exam is that if I recall it correctly, we have only 2 such problems, and each account for 20 points. And if I miss one problem, I lost 20 points, and that really hurts, okay? I understand that. So next time, I will, if we still have such a single choice problem, let's say account for 40%, instead of dividing it into 2 problems, each account for 20% of the score, I will divide it into 4 parts. That is, instead of asking you to solve 2 problems, I will ask you to answer 4 problems. Okay, of course, this problem will be simpler than these problems because I think for a good exam, the grade, the amount of points assigned to that problem should be positively correlated, should be proportional to the complexity, to the challenge, to the difficulty of that question or that problem, right? So that is what would happen in the final, okay? So no more one mistake, 20 points off. But again, it is possible that one mistake, 10 points off, all right? But let me emphasize, this involves numerical calculations. Once you have the answer, you can always compare with those options, okay? If your answer happen to be one of these possible options, then you probably feel very comfortable, okay? Because the number actually agree, okay? That cannot be an accident. That cannot be a coincidence, all right? So if the number, you come up with a number and the number does not appear in any of the part A answers, then probably the best thing you can do is to solve the problem again and try to figure out, is there any way you can get the right answer, all right? Okay. Let's go back to our class, okay? Now, where does side lobes come from in the first place, okay? We know that increasing the size of the window by including more informations into the certain Fourier transforms, we can improve leakage as well as spreading. But the real problem, the real source of the problems behind spreading is that window function you choose has strong effect on the spectral leakage. To reduce leakage, select a window with lower side lobe labels. What does that mean? Here, we use a rectangular function. And after multiplying the original signal, which is a sinusoidal function, this is what we have. And this is frequency spectrum. The problem of this simple signal or this segmented signals is that it has discontinuities which do not exist in the original signal, right? These 2 discontinuities are artificial products. They are the side products of this windowing function. And if you look at the amplitude spectrum of this rectangular function, you see this. They actually look like side lobes, right? They oscillate up and down. If you take the absolute value, it's actually look very similar to the side lobes. So these side lobes actually come from the discontinuity of the window functions. Come from the window function, come from the segmentation effect of the window function, which is an indispensable part of the short-term Fourier transform. So to resolve those problems, what we can do is we choose window functions such as Henning window function or Hamming window function. By using Henning window functions, what we can do is that at the edges, at the boundaries of the window function, we multiply by zeros. So the discontinuity goes away, okay? But because we do not multiply it by a constant, therefore there will be some distortion. To compensate those distortions, especially the further away from the center of this window function, the larger the distortion. So to compensate this problem, we use overlapping window. All right, we use overlapping window. This somehow at the edge of the window, we have less information. But if I let window overlap, then for this part of the signal, it will be sampled twice. Okay, so its frequency component somehow can be recovered, not entirely recovered without any error, but can somehow be retained. All right. Now, this table summarizes popular window functions that can be used. The first is, of course, the rectangular window function, and then the most popular window functions that I know of is Henning and Hamming. Okay. Why do we want to use window functions? We want to reduce side lobes. Okay. Now let's go back to sampling. Okay, sampling operations. We talked about sampling theorems before. Now let's look at it again. Okay. Now sampling theorem. What does sampling theorems tell us? It tells us that rule for perfect sampling and reconstruction. That is, a continuous time signal can be completely recovered from its discrete samples without any loss of information. This sentence is actually very important because we digitalize our signal all the time. Okay, we discretize our signals all the time. In doing that, in order to prefer, I'm sorry, I don't know, okay. In order to guarantee the fidelity of the signal, okay, in order to make sure that no information is lost during the sampling process, we need to make sure that the continuous time signal can be faithfully and completely recovered from its discrete time counterparts, from its digital counterpart, okay, from its digital records, okay, without any loss of information. So that means one of these days, if I want, I can recover everything of the original analog or continuous time signal without any loss of information from my digital records. Okay. Now, key requirement is that the sampling rate, the sample at least twice the highest frequency in the signal. Twice the high frequency of that signal is what we call Nyquist rate. Okay, which means if the highest frequency of that signal, let's say is the frequency of the highest component of that signal, let's say is f star, then my sampling frequency should be at least twice as large as f star, okay? And 2 f stars is the Nyquist rate. That is the minimum requirement for the sampling frequency if I want to have no loss of information during the sampling process. Okay. Now, here, prevention. Use anti-aliasing filter to remove frequency above fx/2. What is that supposed to mean? It means that sometimes, actually, most of the time, what the highest frequency components of a frequency, the highest frequency of the, let me put it this way, the higher frequency of the highest frequency components of the signal is actually infinite. Infinity. Why is that the case? Because if you look at the representation, Fourier series representation, let's say compact Fourier series, it always goes to infinity, right? So Cn will become 0 only when n goes to infinity. That means the frequency of the highest frequency component is actually infinitely large, okay? The only difference is that the magnitude of Cn can become very small, up when n is larger than a certain number, say 100 or 150, or sometimes 10 or 20. It doesn't matter. But theoretically speaking, the highest frequency of the frequency of the highest frequency component of the signal is infinity. I'm sorry. Okay. Now let's go back to where the sampling series is come from the perspective of Fourier transform, from the perspective of spectrum processing. What I want you to know is that if you understand what I am going to do step by step, by understanding the logic behind it, then it means you understand Fourier transform. You have a very good idea of frequency processing. Okay. Now, okay, let's do it. Let's say this is the signal of interest, f of t. Let's assume it is a band-limited signal, which means this is spectrum, okay? And when I say band-limited, I mean its spectrum is limited in a certain range, okay? Here is higher. The highest frequency of its frequency components is actually B hertz, okay? There is no frequency components whose frequency is higher than B hertz. If you prefer to use omega rather than f, then this frequency can be represented as 2 pi b, okay? The unit of omega is, of course, radian per second, all right? Now, what we have here is an impulse train, okay? Now, I can multiply this impulse train with this signal, and this is what I get by performing such a multiplication. Now, the result is a sampled version of the original signal, all right, which is denoted as f bar of t, all right? I think going here from here should not be difficult, okay? So that means if I tie multiply a signal with the impulse strength, what I am doing is sampling operation. Okay. Okay. Remember, the ultimate goal is to reconstruct the original analog signal or CT signal from its digital counterpart when required. In order to do that, how do I do that? Okay. From the time domain, it doesn't seem possible, right? Why does it not seem possible? Because before sampling, my signal actually have infinite numbers of points, right? After sampling, I only have finite numbers of points. How can I recover infinite number of pieces of information from limited number of samples? Okay, how do I do that? By inspecting these two curves, we cannot have any idea, okay? Now, but if we switch our attention from time domain to frequency domain, what we want to do is we want to measure after the sampling operation, the frequency contents of the original signal can be preserved. If they have identical frequency contents, then it means they carry identical information. If they carried identical information, we can always transform one from the other because they have the same information. And if you take the Fourier transform of this signal, this is what happened. Okay, instead of losing information, what you have is first, I preserve the original spectrum. And then, in addition to losing, instead of losing spectral information, I actually have additional spectrum, which was not supposed to exist, right? Because we didn't have this in the original signal, okay? So in the frequency domain, what we have is I periodicalize the spectrum, all right? Here, the spectrum actually become a what? A periodical function of omega, a periodical function of frequency. And its period is actually the sampling frequency, okay? How do I know this is true? It's not difficult. It's not difficult at all, okay? Now, recall that unit impulse function is very important function for automatic control, okay? And if you take the Fourier transform or Laplace transform of that function, this is what you will get. What you will get is a spectrum, amplitude spectrum, a very, very unique amplitude spectrum, because this means this signal has every possible frequency components from 0 to infinitely large, right? And every of those components have equal amount of energy density, okay? They all contribute equally to the synthesis of this signal, all right? So this is this. This is the time domain representation of the impulse function. This is its frequency domain representation, okay? Now, here, what I have is an impulse strength. Now, I can take the Laplace of the impulse strength, and what I will get is this. Similar to this, my DMs is I have dm everywhere from 0 all the way up to infinitely large. But since this is a periodical signal, therefore it does not have continuous spectrum. Why? Because a periodical signal always has discrete spectra. We saw that in the previous lecture, okay? Probably an hour or more ago, all right? Why? Because periodic function always has its Fourier series representation. Once it has its Fourier series representation, it is very easy to see that its frequency components can only occur at the integer multiple of the fundamental frequency. So a periodic signal has to have discrete spectrum, and this is exactly what we have for this impulse stream, okay? Now, if that is the case, that means this impulse stream is Fourier series representation actually look like this, all right? Remember, here, for the impulse stream, the period is t, all right? And omega x here is actually 2 pi over t, okay? Now, this is what we have. This is actually the Fourier series representation of this, all right? Because as you can see from these Fourier coefficients, they are all the same, right? Now, if I multiply the original signal with the impulse stream, this is what I have, right? Now, this is the original signal. This is the original signal times a sinusoidal signal with a frequency of omega x. And this is the product of the original signal and cosine 2 omega st, okay? Now, remember the frequency shifting property. Whenever, let's say this is ft and this is a spectrum, whenever you multiply this signal with a carrier signal, which is cosine omega 0t in this case, a spectrum, according to frequency shifting, is divided into two parts. One of these two parts go to the right, the other goes to the left, right? By the amount of omega 0, all right? So this is the original signal. In order to perform sampling operation, I multiply it by the impulse stream. And what I have is a sampled version of the original signal, all right? Now, this is Fourier series representation, okay? So if I take Laplace transform of this is what I will get, right? If I take Laplace transform of this is what I will get. Why? Because frequency shifting property tells me this has to be the case. You multiply a cosine, you shift the spectrum, okay? Now, if for this one, if I take Laplace transform this term, and I will have this and this, okay? That is the reason why after sampling, okay, sampling converts a CT signal into a discrete set of spectrum replicates, okay? This is a discrete this is a replicate of this. This, of course, is a replicate of this. Replicate means pretty much they are the same, okay? But only happens in different frequency bands. So, and as I said, it actually becomes a periodical function in the frequency domain with a period of omega s. Where does omega s come from? It comes from here, 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 right? So now, remember, my goal is to recover the discretized, recover the original CT signal from its discrete time counterpart. Okay, how do I do that? Okay, the first thing I want to make sure is that the spectrum, the frequency content of the original signal has been reserved. Okay, it is still there. Nothing has been lost. And I'm pretty sure this is the case. It is still there. The only problem is that in addition to the original spectrum, I have some redundant terms. Okay, now how do I deal with those redundant terms? Because they are redundant, I need to remove them. So what I need to do is I can set up a low pass filter to eliminate those high frequency band replicate of the original spectrum. Okay, so sampling is a frequency domain periodicity inducing operation. Okay, this is what we call periodicity inducing, because it convert a non-periodical spectrum into a periodical spectrum. Okay, so sampling is a frequency domain periodicity inducing operation, and Nyquist operation fx larger than 2b is the condition that prevents this periodicity from causing disruptive interference, which is what we call aliasing. Okay, remember that what we need to do is first preserve the original spectrum of the signal and then remove the redundant part of that signal, redundant part of these spectrum components by using a low pass filter. This is only feasible when what? Remember that the size here, I'm sorry, okay, from the original signal, we know that the size here, the size of frequency band is B hertz, right? Because that is the specification of that band limited signal. Is high frequency components occurs at B hertz. All right. Now, since this is a copy of this, so the size of this line segment is also B. All right. Now remember, from here to here, the size of this line segment is fx, right? Because it's fx, the sampling frequency, is the period of the frequency spectrum of the discretized signals. All right. Now, in order to prevent this overlap with this, fx has to be larger than 2b, which is the sum of this line segment and this line segment, the length of this line segment. All right. So fx has to be larger than 2b in order to prevent such an overlapping phenomenon. In this case, because this condition has not been met, this requirement has not been satisfied, so I cannot have a clean cut to remove these redundant components. All right, so they will overlap, and that will create distortions. What distortion? The distortion actually consists of two parts, because we still want to perform low pass filtering to remove this redundant part. Once I perform low pass filter, then this tail will be lost forever. In addition, for this part, which should not exist, which does not exist in the frequency content of the original signal, for this part, its tail actually jump into the frequency bands of the original signals. So the spectrum, which supposed to be this, due to the addition of this, the spectrum become this, all right? And this is the recovered spectrum, which is different from the true spectrum, okay? Now, for this part, the shady side, the shady area, okay, we call it lost head get folded back. And this dark area is what we call lost tail, because after the low pass filtering operation, we can kiss it goodbye. It will never be there, okay? Now, how do we address this problem? Okay, we cannot resolve this problem typically, but what we can do is we use anti-aliasing filter. What is an anti-aliasing filter? It is actually a low-pass filter applied, let me emphasize, before sampling. So before sampling, or let's say original the spectrum is this. Before performing any sampling operations, I use analog circuit to perform low-pass filtering, which means any frequency components of the original signal, which is located at the frequency band, which is higher than omega x over 2, we just simply remove them, okay? Because this lost tail, there is no way we can recover it. But by removing them, by removing this so-called lost tail in the first place, at least it won't get tail, it won't fold it back to create additional distortion, all right? So an anti-aliasing filter is a low-pass filter applied before sampling. It removes all frequency components about half the sampling rate, which is fx over 2, and they cannot cause aliasing, okay? So aliasing error is always the result of insufficient sampling frequency, okay? And aliasing error pretty much is everywhere. So in industry standard ADC card, which means if you measure some signals with a sensor, and that signal is an analog signal, and if we want to send to the computer, you need to have an ADC card to convert analog signal into digital signal. And for many those ADC cards, it actually comes with an anti-aliasing filter whose color frequency you can specify, okay? All right, so what is the purpose of this procedure, of this process of showing that why is sampling theorem is true? Because if you understand each of the steps which is involved in explaining this phenomenon, then you have a very good idea about frequency domain processing, about the true nature of the frequency contents of signals, about how do I process signals using methods such as Fourier transforms, understand the nature of periodical and non-periodical signals, understand what is going on with the sampling process. Okay, let's go one step further, okay? Here, as I mentioned, when you apply sampling, what you do is you convert the spectrum into a periodical signal in the frequency domain, okay? Now, we will observe a similar result in the time domain, okay? We are here, okay? Let's say this is a signal, okay? Now, compare to the signal that we saw before. That signal is what we call a band-limited signal, all right? Because its energy is within a limit band. That is what we call, it is a band limited signal. Now, what we have here is a time limited signal because the duration of that signal is only in tau. Okay? Okay? Outside this segment of which has a length of tau, everything is zero. Now, apparently, it's a non-periodic signal. Okay? You don't see its appearance repeat itself again in the time domain. So let's assume a spectrum look like this, which apparently should be a continuous function in the frequency domain. Let's try to periodize it. Okay, that is, let me introduce additional parts. Okay, which is a replicate of the original signal, but separate from the original signal by an amount of T0. And I just keep repeating doing that. So what I have is this. Now, since this is a periodical signal, therefore its spectrum has to be discrete because it can, of course, represented by a compact Fourier series. If this is the case, then this spectrum will look like this. Periodical signals always has discrete spectrum. It just happened that the Fourier coefficient Dn is actually f omega divided by T0. Well, T0 is the period that we specified in periodicalizing the signal. All right? T0 is the period of this signal. All right? So what happened is that when I convert a signal from non-periodical signal into periodical signal, what I do is I discretize the spectrum. Sampling operation is the opposite. Sampling operation tells us if I discretize the signal, I periodicalize the spectrum. Now, if I periodicalize the signal, I discretize the spectrum. All right? So the operation is in the opposite direction, but pretty similar. All right? Now, so this statement is important. Time domain periodicalization causes frequency domain discretization. This is what happened here. All right? And signals actually can be divided into 4 categories: periodical, non-periodical, continuous, and discrete. Okay, you can have for example, continuous periodical signal, or continuous non-periodical signal, or discrete periodical signal, or discrete non-periodical signal. Whatever it is, to determine its frequency spectrum, you always use DFT. Okay, we saw this before. Okay, let me summarize what we learned here. Let's say what happened in reality is that I have a signal here. I want to know its frequency spectrum. But my computer cannot process the signal in its original format because it has infinite numbers of points. So the first thing I need to do in order to process the signal using my digital hardware is I need to perform sampling operation. Once I perform sampling operation, what happened to the spectrum in the frequency domain is that the spectrum will now become a periodical signal in the frequency domain. Okay, again, I want to know what it is, but this is not acceptable. Why? Because in the frequency domain, this is still a continuous function of frequency. It still is made of infinite numbers of points. My computers, no matter how large it is, it cannot produce infinite numbers of data for me. So what I need to do is I periodicalize that signal. And by doing that, by doing that, this spectrum become discrete in the frequency domain. And then I can ask my computer to produce this part of spectrum for me. With this part of spectrum, for me, I actually understand what is going on here, right? Okay, so in doing so, there are several parameters that require our specification. The first thing is, of course, we need to determine the sampling period. How do I do that? Easy, sampling theorems. Just make sure that my sampling frequency is at least twice as large as the Nyquist rate. All right? All right, that's the first thing. The second thing is I want to periodicize this signal. Originally, it is a non-periodical signal. I want to transform that signal into a periodical signal. To do that, I need to specify a period. Here, this period is denoted by T0. Remember, capital T represent, are shown in this figure, is the sampling period. T0 is another thing. T0 is the period of the signal in the time domain. All right? Once I do that, what I have is I have a what is the space between the two consecutive sampling points in the frequency domain. It is actually here, F0, which is 1 over T0. Why is this the case? Remember, this is a periodical signal whose period is T0. Remember, periodical signals always has discrete spectrum. And those discrete frequency components only occur at the integer multiple of the fundamental frequency. This is the fundamental frequency given in Hertz. Okay? If it is given in radian per second, if you want to give it, it's represented in radian per second, then this spacing is actually 2 pi over T0. So F0 represents the frequency resolution. What do we mean it represents the frequency resolution? It means the resolution we use to view this. Okay? Just like a camera, it has a resolution. The real world is a continual function of space. But if you want a digital picture, you have to discretize the real world by dividing it into a 2D matrix. And each element of matrix actually corresponds to a pixel in your camera, in your digital image, right? And the number of pixels represent the resolution of your digital camera. Same thing happened here, okay? F0 represents the resolution in viewing the original continuous spectrum. The higher the resolution, the clearer the picture. That's for digital camera. Same thing happened here, all right? All right, now we all know that the period of the spectrum is sampling frequency. We know that before, all right? So another thing we need to know that is in the real world is that in using DFT, we prefer the numbers of sampling points to a power of 2, because if we don't do that, the computational cost, the number of computational time is proportional to the square of the number of data points. But if I chose the number of sampling points to be the power of 2, let's say 4, 8, 16, 32, 64, you get the idea. The amount of computational cost is actually proportional to n log n, okay? To help you understand how much computational time you can save by setting the number of data points right, you can see that this curve is n squared, and this curve is n log. And of course, the horizontal coordinate is n. Okay, the variable, the horizontal coordinate is n. Okay, which is the number of data points. If this is the case, there is a very famous algorithm that we can use to implement DFT, and that famous algorithm is what we call fast Fourier transform. Okay, fast Fourier transform is actually an implementation of DFT, but it will only work when this is true. All right, just give you an idea. Okay, now what happens if the data points that I have is not this? Okay, easy. Let's say I have 1, 2, 3, 4. Okay, I have 1, 2, 3, 4, 5. Okay, I can always add 3 zeros behind it. Okay, so it becomes the number of data points become 2 to 3. Okay, and this operation is what we call zero padding. Zero padding is adding 0 to the end of the signal before applying DFT. Okay, all right. Now, what is its effect of zero padding? It increases the number of frequency points in FFT. Okay, when you look at the frequency components, you always remember one thing: the numbers of points in the frequency domain is always equal to the number of points in the time domain, right? No more, no less. Okay. When I have number n, let's say 100 sampling points from the time domain, it means I have 100 pieces of information. Okay. Now, if I want to represent this signal from a different perspective, let's say instead of in time domain representation, I want to use frequency domain representation. Remember, we are still dealing with the same signals. So if in the time domain, I have 100 pieces of information, in the frequency domain, I still have 100 pieces of information, no more and no less. So the more data points I have, the better resolution I have in the frequency domain. Okay. Now zero padding act like an interpolation in frequency domain. Okay, it do not improve actual frequency resolution. If you want to improve actual frequency resolution, you cannot do with zero padding. You have to increase what? You have to increase sampling frequency. All right. Now, so zero padding is like, let's say, when taking a picture by using a camera, okay, and you want to magnify the image, there are 2 ways to do that. One is use optical zoom. The other is use digital rooms. Okay, time is up. Okay. All right. I'll see you in next week. Remember, next week, no exam. Okay, just regular process, regular lecturing. Okay.